Hello and welcome to Electromagnetics for Java engineers, our first episode of AVL Lunch and Learn live on LinkedIn. My name is Glatz. I'm a chemical engineer and a simulation expert at AVL in North America, and I have the pleasure to introduce you today to my colleague, Michael Bambula. Michael is a simulation expert as well and not an electromagnetic engineer, and this is exactly what he will present today. And yeah, I hand it over to Michael and enjoy the lunch and learn.
Appreciate it, Thomas. So yeah, as Thomas alluded, my background is mechanical engineering. I worked in powertrain development, but mostly on ICE and now working in electrification at AVL in the simulation area. So I'm going to present to you guys about our tool that we have and some of the workflows that you can do with it. And it's truly, I'd say, a tool for general engineers who are working on things that require some electromagnetic input in order to get accomplished. So you'll see what I'm talking about later on. So yeah, for the agenda here, I'm going to talk real quick about our little conference that we have in April, end of April. So, that'll be something that you'll get a quick overview on. Then I'm going to talk about our E-Suite, which is effectively the tool set that we use in AVL to analyze e-motors and e-drives. And then I'll talk about our e-motor tool, which is a subset within this E-Suite that allows you to perform electromagnetic simulation and acquire the boundary conditions for thermal analysis or NVH analysis or system modeling. And then I'll talk about some use cases on the thermal system and mechanical side. So real quick, this is our Reimagine Mobility conference that we're having. These are some of the presenters from where they're coming from. So we got people from Ford, Microsoft, Accelera, Cummins, Uscar, Linamar, Novonix. So it's going to be April 23rd to 24th, around 8:30 to 4. It's going to be at Hyatt Place in Novi, Michigan. So here's the address. Who can attend? Pretty much anybody. It's a public event, so feel free to register and go. We can put the link in the chat if you guys want. Why do you want to go? There's going to be presentations from presenters from all over the mobility industry, as you can see from the logos. And what are some of the themes that we'll be presenting on is, e-mobility, thermal management, connected vehicles, power electronics, battery technologies, durability, and NVH. So there's quite a list of topics that you'll learn about and gain exposure to see what people are doing in the industry as well as internally to AVL. So definitely don't miss that. It's less than a month away. So I'm going to jump into our E-Suite now real quick. The E-Suite is effectively a combination of three of our simulation tools that we have at AVL. It's a combination of AVL Excite, AVL CruiseM, and AVL FireM. I need to basically have this slide to show you, because we're going to be talking about these tools throughout this presentation. Excite is a multi-body dynamic simulation tool. CruiseM is a multi-physics system simulation tool. And FireM is a 3D CFD tool. So this is where you can do the electromagnetic calculation as well as thermal studies, detailed thermal studies. So we're going to jump into really what the e-motor tool is, which is a subset of this E-Suite. And the workflow that you can use the e-motor tool in will be used in those three tools that I had mentioned before. So there's a challenge for anyone that's working on electrification propulsion is there's domain experts within engineering. There's people who understand and being mechanical interactions with machines. There's people who understand the system effect, so motor sizing for a given application. And then there's people who understand thermal analysis of e-machines or thermal analysis of, components. And usually those three domains don't really have expertise across. So you won't really commonly find someone who has thermal experience, who understands mechanical development of components and vice versa. And you especially even more rarely would find any one of those people who can understand electromagnetic analysis, because that's a really niche field. So, but all of these three groups need the electromagnetic field results. And so how do you get this without having to rely on your electromagnetic colleagues who may have other priorities? And this is effectively what AVL has here, which is this e-motor tool. And this diagram looks kind of crazy, but I'll walk you guys through it. Is the e-motor tool, you can start with a concept designer, and through that concept designer, it'll automatically set up and leverage AVL FireM for the electromagnetic simulation. So it'll set up the mesh for you, it'll set up the physics boundary conditions, because while you're designing your concept, you're identifying where's the magnet, what are the geometries, and it'll actually create the mesh, the drawing for you and the mesh, and do all of the simulation on the back end for you. So you don't really need to even be a CFD expert in order to set this up. And then with the results of this electromagnetic simulation, then you can carry it over and start doing analyses in those three tools that I had mentioned earlier, CruiseM, FireM, and Excite. And these are these studies that I'm talking about where you want to understand your motor requirements and viability within a given application. That would be your system modeling. You want to understand your thermal behavior of the motor. That's your CFD FireM run. And then your rotor dynamics and acoustic analysis, and that's your Excite analysis. So the workflow that we do with the e-motor tool I mentioned, there's the concept designer. That's where you can define, you know, your torque, your speeds, your safety margins, things like that for the motor. They're very high level concepts that you could define. I'll go into a little bit of how that looks in the next slide. The other two portions of the e-motor tool is the geometry assistant. So I did mention once you finish your concept, you can start defining your geometry and create a sort of a drawing of your motor, and that will then be meshed and sent to the EM model assistant for the CFD run for the electromagnetic calculation. And anytime through these steps, you can also deviate a little bit and import your own motor drawing that you have, or you can even import your own mesh to get that automated electromagnetic run. And so, yeah, this is a workflow that's helpful, but not fully rigid, that forces you into doing a certain thing and you doing things a certain way. You're able to sort of include your own whatever resources you have available. Every organization's different. You may not even have access to drawings. You may not even have a CAD of your motor yet, so you may not even have a mesh. So it's super useful. And as I mentioned, this is the concept designer. So you can put your voltage, your, as I mentioned, speeds, torques, and it'll effectively, in a high level, give you some attributes from your motor. So you'll be able to see an efficiency map, you'll be able to see a couple other things, and you can also add these sort of constraints and design customizations while you're in this step of the concept designer. And these use some internal, I guess, intuition within the tool. Some people would call it, I don't know, machine learning or whatever. But with that, you're able to sort of quickly screen and filter and field designs of your e-motor if you're starting really from a concept phase. So it's extremely useful in that portion of your development. Then you have the geometry assistant. So this is where I mentioned you can start developing the motor drawing, so to speak. So it's very, I'd say, geometric. You got to define your geometries pretty much in here, and your materials, and you know, basically almost all parts of your motor. So you can see here there's the machine configuration. So you obviously have to define this, and your pole pairs, and then you have your stator that you would define the geometries. You have your rotor that you would define as well. So, you know, magnets and angles, half angles between the magnets, things like that. And once you finish this step, you'll end up getting a drawing that will be output. And this is where you have your ability to mesh it. And you can see now when I'm describing this geometry definition phase, how you can get a drawing of it, and then you can effectively mesh that. So automatically, the tool AVL FireM will mesh the drawing, and it'll do it with the best practices, so you don't have to worry about your mesh sizes and, you know, what type of mesh you want to use. And so yeah, it's a quite a user-friendly thing, especially if you don't have that CFD domain experience. You likely don't really understand the differences between, you know, polyhedral meshes or tetrahedral meshes, and, you know, prism layers and things like that. So the next and final step is the EM model assistant. And so this would be where the run would be performed, and you have these outputs that you can then say, I want to use these in the downstream in these other tools. And so you'll get effectively your your losses that could be that are boundary conditions to your thermal simulation. You'll get your maps that you can use for your system model, which I'll show a little bit how that is. And you can also get your forces that you would use for your NVH study, acoustic study in Excite. So overall, this is AVL's e-motor tool. This is the picture again. And in that box is effectively the user-friendly portion of this. And if you had to try to acquire and perform this yourself, likely in your organization, you do it with another external tool, and then you carry some results over and try to use that and downstream in a separate tool that doesn't really integrate well. This is where things become tricky. You may not know every boundary condition you need. You may not know how to use one of the tools within your workflow. You may have to rely on a colleague, and that takes time, and that takes, a lot of effort in the org, where effectively our e-motor tool enables the general engineer, which is the theme of this presentation. So we're going to talk about some use cases here. So this is that map again, and I'm isolating it down to the thermal analysis. So we're only going to be talking exclusively in 3D CFD. So this is the workflow that you would do for a thermal analysis. So you guys who know CFD, you understand you have a 3D CAD, you do the mesh. Within our mesh, during that meshing process, you can also then later on define your materials, and this step would be where you would use the losses that you get from the electromagnetic simulation, the e-motor tool, to map those out in the 3D boundary conditions for the CFD, and then you can do your cooling study and then obviously analyze your results. So effectively in the e-motor tool, what you're doing there is you're taking your power losses and your losses within the stator windings and the rotor core, and you're effectively mapping those as heat sources within your e-motor. And that's the use of the e-motor tool that we talked about earlier. Within our 3D CFD tool, obviously you're able to define your different materials. There's a very automated mesh generation that will occur in there. So it's a pretty user-friendly thing from a CFD standpoint. And with that, you're able to study all of these different thermal management strategies for the e-motor. So you could do oil spray studies, you could do water jacket or oil jacket studies, you could do convection, cooling, forced convection or free convection. So it all depends on what your motor architecture is in your application. But a FireM is a general purpose CFD tool that's able to accommodate a wide range of motor types for thermal management. So this is a study where we're going to talk about thermal analysis of a water jacket within the e-motor. And there's a couple of different designs that you can do here, and what you're seeing here is basically the meander shape of a water jacket within the motor. So you're seeing the cooling channels going back and forth lengthwise of the motor. With FireM and with the e-motor tool, with the appropriate boundary conditions, you're able to do radical channel design analysis, and then you can see what the temperature looks like on your magnets and on your rotor, and effectively understand if a design is better or worse for your given application. You can see here, I wager that the spiral shape looks like it keeps much more of these two subcomponents, the magnet and the rotor, cooler than your meander shape. So you'd also have to do a trade-off there and understand how does that impact my weight. There's probably more mass here, and things like that. But that's all up to you as the engineer to decide for. The other thing we can do is oil spray analysis. So this is another thing that we see in the industry that is happening, is there's a large interest in understanding this, and this is a very complicated CFD because you have spray impinging on the windings, and this is something that is that could be a very sensitive factor for thermal management within your motor, because it's seen as more of a feature in a way. So this is something we do continuously here in AVL and FireM, and this is where I mentioned the sprays on the windings, and Yeah, so with that, you would want to understand your oil volume fraction on the winding surface. How wet is are the windings? What's your heat transfer distribution on the windings and near the wall? And then effectively your structure temperature is the macro KPI for this. So this is something that you would need the electromagnetic tool as well to, transfer those losses over and get your proper thermal boundary conditions, and then you can study that with the CFD and understand your oil cooling margin. And then from there, you can understand your oil flow rates and things like that, and, really do some detailed engineering work there. So the next use case that I'll go over is the Cruise M, the system modeling one. So we kind of drew a little box around here on the left side. What you'll see here is because we have a 3D tool and a 1D tool that we self-develop at AVL. What will happen here is we have data exchange that occurs, so-called simulation results exchange. And what happens is you are able to identify your elements and your connections in the 3D CFD and create a representation of that in Cruise M automatically, as well as your boundary conditions that you would have input. So your material properties will carry over, your geometries, your masses, things like that will carry over into the system model. And I know it's sometimes difficult for people to get a grasp of system modeling because it's sort of an abstraction of the 3D, but this is hugely helpful to be able to sort of abstract down to the 1D world after you've done your 3D study. And I'll show you how this is useful with this use case. So in the end, it'll automatically calibrate your thermal parameterization of the model, and you'll have an adequate, a representative 1D model of your 3D motor that you just did. And it'll look something like this. So you can see your 3D e-motor. We've been looking at 3D results throughout this whole presentation. This is the 1D diagram of this. So you can see you have rotor, magnet, winding, stator, housing, shaft, air, and you have your different modes of heat transfer around here. And then you have a cooling liquid path down here that cools the stator, the housing. And effectively, you can use that in a system level model like this vehicle here with the battery and the e-motor here highlighted. And it could look something like this, where you have a little bit more of a detailed cooling channel occurring here. So you have, heat exchangers, pumps, chambers, and when you try to look at that, it'll look like what we had imported from the FireM simulation. So that's effectively how your e-motor thermal system would look. And I'll talk in here about probably a little bit more of a detailed model that was developed and how you would use some of those losses that I had mentioned earlier in the presentation that you get from the electromagnetic simulation, how you would utilize that in your system model. So you can see here we have an e-motor, and I'll highlight some of this to show what the different regions are. So there's the oil up here, there's your stator, there's your rotor, and you have air over here. And effectively, what we will be doing is putting our power loss into this heat stator boundary condition here. And you'll see here in this slide, we have the e-motor that's giving out a speed and a torque lookup that gives a heat loss to the heat stator. And you would get this map, this power loss map from the e-motor tool. So this is what I would say is one of the biggest things as a system modeler that you're wanting when you're developing an application that uses an e-motor in system level tool. You need these losses, or else you're not going to have accurate representation of your thermal behavior of the e-motor. And this is important because we're going to show a study here where you want to understand your thermal margin, because you run the risk of potentially demagnetizing your motor, or you just have a loss, like an energy loss due to an increased cooling requirements. So this would be something you get, and you'd use this in this way. You just connect it to your boundary condition here. And this is the other boundary condition where we have the heat transfer convection coefficient as a function of speed, and that's from the oil splashing. So you can see here we have our oil splashing here on the top, and it has a energy transfer to the front winding. And you're going to change this heat transfer coefficient here, and it'll be a function of speed, and you can see the heat transfer coefficient increases as the speed increases. So you're imagining that rotor spinning around, the e-motor spinning around, and the oil splashing like we showed in that video, and you would have a higher heat transfer coefficient as the speed increases. So this would be something that you can get as well through CFD, and this would be a crucial input if you have an e-motor that's using oil cooling on the windings. So this is that study that I was alluding to. This is a study where there was a base electric vehicle, and then they did a second case where they reduced the e-motor size. And then they did another study where they reduced the e-motor size and had a two-stage gearbox. And so effectively what you see here is on the baseline, the black line gave somewhat of a low temperature, but when they downsized the motor, you had an increase in temperature. And then they were wondering, how do we make that temperature decrease again back to what it was? You know, we see the benefit of downsizing the motor, but we don't want to give away our thermal margin. And so then what they ended up doing was adding the two-stage gearbox in the model. And you can see now the temperature, at least on the windings, have fallen lower than it was if it was just a downsized motor. And you can see here also the magnet temperature also went down a little bit. It didn't go down as low as baseline, but it went down enough to where you obviously aren't running a risk of demagnetization. But it's definitely a lot better than just a downsizing of the motor geometrically. So that's a study that you would want to do, where you could potentially look through a supplier catalog and find a smaller motor and then say, maybe I should approach this from the transmission side, maybe I shouldn't. So yeah, and this is effectively our workflow that we did. So you saw we did we had our CFD that we ran, and we sent that to Cruise M for the system model. And yeah, so you're determining your heat losses through the electromagnetic simulation. You're considering your fluid flow and your temperatures on the rotor and the stator, and you're using those results and extracting them and creating the system model, thermal model that I showed you guys earlier. And that's all in a somewhat automated fashion, from the e-motor tool to the thermal network generator, from the CFD results to the system model. All of that is in a wizard format, wizard-like format. And then you can optimize your thermal design. And so this is the final use case. I don't have a lot of time left, I guess, but I'll just briefly touch on this. This is something where you would use the e-motor tool for the NV study. So you can get your electromagnetic forces for the stator teeth. And those are one of the key excitations that you need to consider when you're simulating e-drive NVH behavior. And really, a lot of people are unable to acquire these. They rely on another team to give them these forces, and the e-motor tool will allow you to do that. The other thing we have in Excite is the ability to understand your inverter and your power electronics, basically your power electronics influence on your e-motor. So we have this thing called this e-motor joint, so to speak, and that's where you're able to send these results back and forth and do your NVH study and really get a much more accurate and realistic representation of your study in a dynamic simulation. So that's pretty much the end of my presentation. We have 2 more that we're going to do of these lunch and learns, one every week. So next week on Wednesday, April 10th, we'll do fuel cell degradation modeling in Cruise M. This is an industry-leading capability that we have, where we have degradation mechanisms for fuel cell in Cruise M. I'm not aware of any other vendor that has this. And then the week after that, on the 17th, we'll do our e-axle design, robust e-axle design with Cameo and Excite. So effectively, that's an optimization tool where we'll understand our manufacturing tolerance and sort of put that within the scope of NVH drift and things like that. So you want to make sure your design is robust, and if you have some tolerances that don't go the way you think they're going to go, you're not going to have an NVH disaster. You have something that's more manageable in terms of your tolerance stack. So that's all I have for the presentation. And if you guys have any questions, as always, feel free, throw it in the chat. Otherwise, yeah, that's pretty much all I got.
Yeah, thank you, Michael. You're perfectly on time. As mentioned, reach out in the comments directly in LinkedIn chat, or see us live at the conference on the 23rd and 24th in Michigan. And with that, I'd like to conclude today's Lunch and Learn, and see you again hopefully next week.
Yep.
Thank you. Bye-bye.